Hello and welcome to this video. In this video we'll be looking at coplanar vectors and ratio theorem. So what are coplanar vectors? Vectors are said to be coplanar if they lie in the same plane. Now any two vectors can be on the same plane, just like there can be a line that goes through any 2 points. But for the third point, it remains to be shown that those 3 points are collinear. Similarly, it remains to be shown that 3 or more vectors are coplanar. And so that means there's a condition that those vectors have to satisfy, and that's what we want to look into. Okay, so say we have these 3 vectors that you can see on the plane. Because they lie on the same plane, that means the normal to the plane will be perpendicular to all 3 of them. In other words, the normal to this plane is perpendicular to all vectors that lie on this plane. So the question is, how do we get the normal to the plane? We can decide to pick any 2 vectors. So for example, we could pick these 2, this and this, find their cross product, because you know that the cross product of 2 vectors gives us a vector which is perpendicular to both of them. And so in fact, the cross product of those 2 vectors will give us the normal to the plane. And now we check if this normal is actually perpendicular to the third vector. How? By finding the dot product of the normal and the third vector. And if that dot product is 0, that means those vectors are perpendicular, and therefore the 3 vectors are coplanar. Okay, let's see how that would look in an example. Okay, so we've been asked to show that these 3 vectors are coplanar. 3, 4, 1, 3, negative 1, 2, and 1, negative 2, 1. Okay, so we could let A be equal to 3, 4, 1, B equal to 3, negative 1, 2, and C equal to 1, negative 2, 1. So we go ahead and find the cross product of any 2. You could pick A and B. So you find the cross product of A and B, it will be 3, 4, 1, cross 3, negative 1, 2. We looked at how to find the cross product in the previous video, so you should be familiar with that. And I'll just jump right to the answer, which is 9, negative 3, negative 15. Okay, so that's the cross product. Now we check if this cross product is actually perpendicular to C by finding the dot product of the cross product and the vector C. And this would be 9, negative 3, negative 15 dot 1, negative 2, 1. And when you work that out, that should give you 9 plus 6 minus 15, which is 0. That would mean that the vector A cross B and C are perpendicular. That means the normal to the plane that contains A and B and the vector C are perpendicular. Therefore, the vectors A, B, and C are coplanar. And that's how you would work that out. Okay, so we looked at coplanar vectors, and now we want to look at ratio theorem as well. So say this is our origin, and we have the point A and B. So point A and B form a line segment. There's a line that goes through the points A and B, and there's a point C which divides AB in a certain ratio, lambda to mu. And so we want to find a way we can determine the position vector or the coordinates of point C once we know the ratio lambda to mu and the coordinates A and B. So let's call this vector OA, small a, and let's call this vector OB, small b, and okay, also OC, let's call it small c. So we want to find OC, which is a small c. We know that AC, as you can see, is a certain fraction of AB, lambda out of lambda plus mu times AB. And we know that OC, which we want to find, is in fact OA plus AC. So this would in fact be A plus lambda out of lambda plus mu times AB. But we know that from our knowledge of vectors already, that AB is in fact OB minus OA, which is B minus A. And so then when you simplify this, you actually get mu A plus lambda B out of lambda plus mu. And so that is the expression for the position vector of point C. Notice that mu, which is associated with B, when you talk of AB, is actually being multiplied by the position vector of A, and lambda is being multiplied by the position vector of B, and then we're dividing that by the sum of the parts the ratio is splitting. Now we want to look at internal and external division as well, because a line can be divided internally or externally, and we're going to demonstrate that. So we already looked at what we saw in the previous slide was in fact an internal division, and this is one where you have the point that's dividing in between the 2 points of concern. So we have AB being divided by C. C is in between A and B, and this division is in the ratio lambda to mu. However, the point C can be either to the left of A or to the right of B, and that's what is called external division. For example, in this case, we have the point C dividing A and B externally, and the ratio here is lambda to mu, but then one of these is going to be negative. Now personally I prefer that you move from, if we're dividing AB, order is important. If we're dividing AB, so we'll move from A to C, and then from C to B. And because from A to C is the movement to the left, this would be negative lambda to mu. However, you could make either of them negative. It's your choice. You'd still get the same answer during calculation, because now in this case it's going to be OC is going to be, just have this as negative lambda, and mu, this is going to be negative lambda times OB plus mu times OA out of negative lambda plus mu. Since negative lambda is associated with A, you multiply it by the position vector of B, and vice versa. And so you could also have a scenario where you have A, B, and then C to the right of B. And if you're dividing AB again, like I said, we move from A to C, and then from C to B. So this is going to be positive lambda and negative mu. So this would be lambda to negative mu. And so then this would be OC is equal to lambda times OB plus negative mu times OA divided by lambda plus minus mu. Yeah, so I believe when you consider the directions, movement from the first point to the point that's dividing, then to the last point, it gives you a better idea and a better representation of which is going to take the negative sign. Notice that in this example you move from A to C, and then from C to B, you're moving in the same direction, and so in this case everything is positive. Yeah, so that's ratio theorem, and in the next video we'll be looking at some examples.